All right, today we are diving into one of the most incredible high-stakes biological processes happening in your body right now, the coagulation cascade. And look, this isn't just about how you get a scab. This is a microscopic emergency response team that literally keeps you from bleeding out. It's amazing.
Think about the last time you got a paper cut. Annoying, right? You barely notice it, but in those first few seconds, your body launches this unbelievable, dramatic, high-speed biochemical soap opera just to plug that tiny little leak. It's a true masterpiece of control, speed, and just brute force.
So how does it all actually work? Well, at its very core, the whole thing is a perfectly orchestrated, life-saving chain reaction.
Your body doesn't just hit some big red stop bleeding button. I mean, that would be total chaos. Instead, it uses something called a cascade. And the best way to picture it is like a row of dominoes. One protein, a zymogen, is just kind of sitting there, inactive. It gets a little nudge, and it activates, turning into an enzyme, specifically a serine protease. And what does it do? It turns around and activates the next zymogen in line, which then activates the next, and on it goes.
And this is where we see the sheer, mind-blowing power of this system. This cascade creates massive amplification. If each domino can knock over, say, 10 more dominoes, you get this exponential explosion of activity. In just 4 simple steps, a tiny initial signal can be amplified 10,000-fold. It's how your body turns the whisper of an injury into the absolute roar of a full-blown response.
Now, every good story needs an inciting incident, right? For our coagulation story, that's the trigger. But as you're about to see, this trigger, well, it comes with a built-in problem. A big one. Okay, so the very first alarm system is called the extrinsic tenase complex. We're just going to call it the trigger. Now, when you damage a blood vessel, a protein that's normally kept hidden on the outside of your vessels, called tissue factor, is suddenly exposed to your bloodstream. This is the tripwire. This is the red flag that starts everything.
So here's the play-by-play for how this trigger works. First, that tissue factor gets exposed. It immediately finds a partner that's just floating around in the blood, factor 7A. Together, this dynamic duo forms an active complex, and their only job, is to find another factor, factor 10, and switch it on. That creates factor 10A. The A just stands for activated. Simple, right? This is your body's first, super rapid response.
But here comes the plot twist. This incredibly important first step, it has a fatal flaw. And here's that flaw. The trigger, this whole extrinsic tenase complex, is designed to be shut down almost immediately. There's this molecule called tissue factor pathway inhibitor that just jumps in and slams the brakes on the whole process. So that raises the crucial question. If the initial alarm gets silenced so fast, how on earth does your body build a stable, lasting clot?
The answer lies in the system's most elegant little trick, a tiny but all-important spark.
You see, before that trigger gets shut down, it manages to create a tiny, almost insignificant amount of the master clotting enzyme, thrombin. Now, you might think this little puff of thrombin is useless, but it's not. This isn't the main event. This is the brilliant plot twist that changes the entire story.
This tiny amount of thrombin, it acts as a spark. It turns around and ignites several other key factors, specifically factors 5, 8, and 11, that belong to a different part of the cascade, what we used to call the intrinsic pathway. It's like a crossover episode. This spark is the critical link that kicks the real powerhouse of coagulation into gear.
And this is how we know just how important this second phase is. If you look at patients who are deficient in factor 12, which was once thought to start this whole intrinsic pathway, they have no bleeding problems at all. But patients who are missing factor 8 or 9, the very factors lit up by our thrombin spark, they suffer from severe hemophilia. This tells you everything. That spark-ignited pathway isn't a backup plan. It's the main event for building a proper clot.
So, the spark has been lit. The fuse is burning. Now it's time to unleash the full force of the system, the thrombin burst.
So that thrombin spark we just talked about, it goes and ignites a brand new complex, the intrinsic tenase complex, which is made up of activated factors 9 and 8. Now, if the first complex was the trigger, this new one, this is the amplifier, and its job is to take that tiny initial signal and just crank it up to 11.
And I mean really crank it up. The activity of this amplifier is just mind-bogglingly higher than the initial trigger. We are talking up to a 10,000, 100,000, sometimes even a million-fold increase in how fast it can activate factor 10. I mean, look at this chart. It completely dwarfs what the trigger could do.
So what's the result of all this insane amplification? Well, you get an exponential, explosive production of thrombin. This isn't a spark anymore. Oh no, this is a full-blown thrombin burst. It's the climax of the cascade, and it generates all the thrombin you need to build a strong, stable clot.
And this is exactly why that burst is so critical. A normal clot, one that's fueled by a thrombin burst, forms this dense, strong, cross-linked mesh of fibrin fibers that actually plugs the leak. But in a condition like hemophilia A, where the amplifier is broken, you just get this weak, flimsy, fibrin structure that can't really do the job. The burst is what provides the power for a proper repair.
Okay, so we've seen the what, the trigger, the spark, the amplifier, the burst. Now let's dive into the truly elegant how at the molecular level. And it all comes down to this really clever trick performed by vitamin K. A lot of these clotting factors have a special section on them called a GLA domain. And the absolute easiest way to think about this is as a molecular grappling hook. Its whole function is to make sure these powerful enzymes don't just float off aimlessly in the blood. No, they need to be concentrated right there at the site of the injury, on the surface of your activated platelets.
And this is the biochemical magic right here. When these factors are first made, this domain has regular old glutamic acid residues, or glue. They're not sticky. Then, an enzyme that is completely dependent on vitamin K comes along and adds a second acid group to it. That turns glue into GLA, or gamma-carboxyglutamic acid. And this modification gives it two negative charges, making it a perfect little magnet for a positively charged calcium ion. That calcium then acts as a bridge, anchoring the whole clotting factor right onto the negatively charged surface of a platelet. So no vitamin K, no sticky grappling hook. It's that simple.
This idea gets driven home when you look at the actual concentrations of these things in our blood. We have massive amounts of fibrinogen, that's the final building block, just sitting there ready to go at 3,000 micrograms per milliliter. But factor VIII, a key part of the amplifier, it's present at just 0.1 micrograms per milliliter. That's 30,000 times less. It just proves you only need a tiny, tiny amount of the early amplifiers to unleash the vast reserves of the final material.
Okay, so let's wrap this up with the key takeaways. First, forget the old model of two separate pathways. Think of it as one integrated system with two main phases, a fast but short-lived trigger and a massively powerful amplifier. Second, the two phases are connected by that tiny but absolutely critical thrombin spark. Third, this system unleashes an exponential thrombin burst to create a really strong fibrin clot. And finally, the whole thing is physically held together right at the injury site by vitamin K's incredible molecular grappling hook trick.
I mean, it is an absolutely stunning piece of biological engineering, right? A perfect balance of speed and control, all designed to save your life. But that raises one final, crucial question. This emergency response is incredibly powerful. So what happens when it can't be shut off? What happens when the clot starts and just doesn't stop? Well, that's a story for another time.